Hello everyone. Probably last lecture on thermal stresses, I hope. Okay, we shall make it the last one, and we have done many problems and sufficient number. So in any case, I hope you also shall go through few problems and solve them and understand the concept, and if there are any difficulties, you should approach us always. Okay, unless you put some effort, it won't become final. So you need to gain confidence only by solving a number of problems. Okay, one such problem what I intend to solve today is 10/8/34 July 2013. You have already problem with you. The problem goes like this. I shall quickly read for you, and along with me you can also read it loudly. A composite bar made up of aluminium and steel is held between two supports as shown in figure. This is the figure what? Yeah. This is steel portion, this is aluminium, and these are the two supports. Okay, rigid supports, normally supports are rigid. Okay. The bars are stress free at a temperature 42 degrees centigrade. That means this is 500 mm, 250 mm. These supports now, they are neither pressing them or they are neither pulling them at 42 degrees centigrade. So this is 500, this is 250, just they are there and they are not subjected to any load. Or in other words, what does it mean? When there is no load, they are stress free. They don't have any stress at 42 degrees centigrade. Okay. Okay, what will be the stresses? In the two bars, which is the temperature drops to 24 degrees centigrade. I think the first time we are solving a problem when there is a contraction. Okay, the earlier it was 42 degrees centigrade. Now the temperature is dropped to 24 degrees centigrade. As we know that when they have cooled any material, so its dimensions will decrease. See here, the length of this 500 and 250. So that will decrease. This bar will contract. Its length becomes less than 750 mm. So they are away from the support. But the supports, what they do, that they don't allow it to happen. They pull it. They pull the bars on either case, either side, and make the bars in contact with that. Otherwise, the very purpose of making this bar will fail. Okay. So now, so the first one is the supports are unyielding. That means the supports, they are really rigid. They don't move at all. They don't move at all. Okay. So that's what is the meaning. The support will remain here only. The support will remain here only. And this is going to contract. And the two supports are pulling it. And what are the stresses? That is the first case. So I have just listed the other dimensions which are mentioned there. And I shall go to the first case now. So before the first case, I have made certain calculation, delta T. Okay, the change in the temperature is final temperature is 24 minus 42 is minus 18 degrees centigrade. Okay, now what is the free expansion, what I used to call it? So in this case, it is the free contraction. But anyway, I shall continue to have expansion only, free expansion. That will be with minus sign. That indicates that it is not really free expansion, it is contraction. So free expansion is delta L of steel, the alpha of steel, the length of steel multiplied by delta T of the steel, delta T, the change in the temperature. So this gives you what is the change in the length, delta L S. Are you ready with the answer? This
minus 0.108.
Minus 0.1 108 mm. Okay, similarly, the aluminium for this alpha of aluminium, the length of the aluminium and temperature change. So this is also minus, how much it is?
Minus 0.108.
Same, minus 108.
108.
Okay. Okay, here the length is exactly half and alpha is double, therefore both of them are equal. So the total value is minus 0.216 mm. 0.216 mm. This is the total. Okay, now for the first case, suppose unyielding, that means they are not moving at all. that is the meaning of that, unyielding supports. The supports are really supports. Okay, so supports, what do? Since the bar contracts, that is not allowed to happen. So by doing what? The supports pull the bars at the two ends, and therefore the tensile stresses are induced in the bars. So how much is the magnitude? What is this delta L total? I want to remove that minus sign now. Therefore I have put modulus. Modulus, that is nothing but 0.216. That is the extension what this P is responsible for. So delta L total, I shall remove this and I can write it as, it is 0.216. So this side it is being put at P and this side also it is being put at P. Okay, therefore, so P into Ls upon ASVS plus P into LA upon AAEA. So you calculate what is the value of P?
7.08 kilo.
7.08 into 10 raised to 3 Newton. Okay, so then once you know the P, then you can easily calculate what is the stress in the steel. That is P upon A, 7.08 into 10 raised to 3 divided by 160. 44.29 megapascal or Newton per millimeter square, and that is tensile in nature. And similarly, P upon aluminium, 29.5. So many Newton per millimeter square. So now coming to the second part. What is the second part? Second part of the problem. Go back and read it. The supports come nearer to each other by 0.1 mm. So these are the two supports. This is one and this is the other one. They come closer. So it may be both of them may move or one of them remains stationary, and let me assume that only the right hand side support comes closer by 0.1 mm. So now it is very similar. So what is the contraction prevented? So the contraction which would have taken place is 0.216 mm. So out of this 0.216 mm, because of the movement of the support, so 0.1 mm, there is no need to contract. So therefore, the contraction prevented is delta L total minus 0.1. That is 216 minus 0.1 is nothing but 116 mm. So since I have written already on the left hand side contraction, therefore I am not putting minus sign here. Okay, so here I am not saying that it is free expansion which is minus. So here I am already calling it as contraction, therefore I am not putting it as minus. So it is 0.116. Supports prevent contraction by pulling. Therefore tensile stresses in both bars. So how much? That is equal to 0.116 mm, which is equal to P into Ls by S. Everything remains same. I hope you will be able to calculate what the value of P. 3.80 into 10 raised to 3. Okay, everything same. So therefore you calculate what is the stress in the steel, stress in the aluminium, and I want you to complete that. Okay, this is for 12 marks. So all the problems on thermal stresses are they are almost identical. Calculate what is the free stress or free expansion and check so whether all the entire free expansion is prevented or part of it is prevented. Then how much is prevented? That is equal to P into L divided by A into E if you have only one. Otherwise if you have like this, then the portion P into Ls like that. This is how you will get so many parts like that. Okay, the problem remains same. Okay, now let me go to another one, the problem which you already have with you, and that is something interesting. So it is not only thermal stress problem, you have something else, what is called as composite bars. Composite bar which is also subjected to load. Here I have force also and the change in temperature also, and therefore if I have two effects, then I am supposed to find out what is the total effect. What I do is I apply principle of superposition. So therefore I take only load, then calculate what is the effect. Then I take only temperature change, then find out what is the effect. and then to get the total effect I add the two effects, and therefore I am applying what is called as principle of superposition. The problem goes like this. This is June 2012. June 12. This is also 10 MB34. Don't worry about the scheme. 10 indicates only in which year the syllabus started. The problem goes like this: a horizontal rigid bar. Please underline that, rigid bar. Rigid is the one which does not undergo any change in length. A horizontal rigid bar AB weighing 200 kilonewton. Its weight is 200 kilonewton. That is hung by 3 vertical rods, each of 1 meter length and 500 millimeter square cross section area, as shown in figure question number 2C. Okay, so unless you see the figure, suddenly you will not be interested to go through the remaining part. So let me draw the figure. So what you have is something like this. You have a heavy weight. This is the horizontal bar, 200 kilonewton. The weight of this is 200 kilonewton. So when you mention that horizontal bar, that means this bar will always remain horizontal. That is why it has been mentioned horizontal bar, and it will never become later on something like this. This kind of a position is impossible, or you cannot have like this. So this will remain horizontal all the time, 200 km. Okay, so how will it remain in this position? By means of, it is hung by, okay, so I can have a bar, I can indicate it by, say something like wire. Please remember, they are not lines, they also have cross section. Okay, so now you have support here. This is ceiling or support, they are hung. And this is copper, and the middle one is steel, and the end one again is copper, and sometimes it may be something different also, no problem. And all of them are 1 meter. Well, before the application of this 200 kilonewton, please remember 1 meter is before the application of the load. The moment I apply 200 kilonewton, naturally, this is subjected to tensile load, this also is subjected to tensile load, this also will be subjected to tensile load. Probably it will come down. And let me show it. I am showing the exaggerated expansion. This is what is going to happen. This is going down. So why? Because this is subjected to tensile force, this end is fixed, this load is pulling it down, therefore this is subject to tensile force, this also. The only thing is, each one of them is not subjected to 200 kilonewton, because this copper, this steel and this copper, all of them are sharing it. They are sharing the load in this copper wire, the load in this steel wire, the load in this copper wire or bar, whatever. All of them together is equal to 200 kilometers. Since the area of cross section of all the bars is same, it is 500 millimeters square. All of them, I can say A of copper, A of steel, A of that. Okay, so one thing is sure now, when it moves, this will come down, and this delta L is the expansion of both copper wires and also steel wire. If they undergo the different expansion, then this bar will not remain horizontal, it will become inclined. If it undergoes a larger extension, a smaller one and still smaller, in that case it may become like this. This is not allowed. So this moves like this and remains horizontal, and therefore each one of them undergoes the same expansion. Okay, so let me assume that, say this is number 1, and say this is number 2, and say this is number 3. Wire number 1, wire number 2, wire number 3. So wire number 1, delta L is also equal to P P1 into L divided by A into E1. Since L and A are same for 1, 2 and 3, I am writing it like this. This delta L is also equal to P2 into L divided by A into E2, where 2 means steel. Similarly, this is also equal to P3 into L divided by A into E3. Of course, this and this they are identical. P1 is equal to P3. Okay, so therefore, making use of this immediately, so I observe that P1 is equal to P3. This is the first thing what I understand. You compare this is equal to this. L cancels, A cancels, E3 is same as E1. E3 is same as E1. And therefore P1 is equal to P3. Because this also is copper, this also is copper. The Young's modulus of elasticity of copper is same, and therefore this and this they are same. Let me write here 3 and say Y as E1 is equal to E3 is equal to E of copper. Okay, so now then what is the relationship between P1 and P2? L cancels, A cancels. Therefore, P1 divided by E1 is equal to P2 divided by E2. So from this, I shall find out P1 is equal to or P2 is equal to. Let me find out P2 is equal to, or let me have all in terms of 2. So P2 is equal to what? E2 divided by E1 multiplied by P1. So what is E2? Let me see here the values that have been given. I didn't complete the reading part of it, and I hope you can complete that reading part. E of copper is 100 and E of steel is 200. E of steel. Okay. So this is equal to what is E2? E2 is nothing but E of steel, that is 2 into 10 raised to 5 divided by E1, the copper, that is equal to 1 into 10 raised to 5. This into E1. So 10 raised to 5, 10 raised to 5 cancels. This is equal to 2 times P1. So what relationship I have? P2 is equal to 2 times P1. 2 times P1. Okay, I know what is. Then this P1 plus P2 plus P3. What is that? P1 plus P2 plus P3. All this is together 200 kilonewton. The total weight, whatever is being applied, part of it is P1, part of it is P2, part of it is P3. But the total weight P1 plus P2 plus P3 is equal to 200 kilonewton. P1 is what? P1 is P1 only. What is P2? P2 is 2P1. And what is P3? P3 is P1. So 2 times P1 plus 2 times, okay, P1 plus 2 P1. This is 200 kilonewton. And what is this? This is 4 P1, and therefore P1 is equal to 200 divided by 4. This is equal to 50 kilonewton. 50 kilonewton. Okay, so therefore, what is the stress in sigma 1? Stress in sigma 1. Sigma 1 is how much? 50 into 10 raised to 3 divided by 500 millimeter square. How much it is? 100. This is 100 Newton per millimeter square. Is it tensile or compressive? This 200 kilonewton, as you understand, you can feel it also. This 200 kilonewton is being pulled. This also is extending its length. So therefore, all these are tensile. This is tensile. And what is sigma 2? Sigma 2 also. Sigma 2. Sigma 2 is nothing but P2 divided by A2. What is P2? This is 100. Because P2 is 2 times P1. This is 100 into 10 raised to 3 divided by 500. This is 200. This is 200 Newton per millimeter square. This also is the tensile. And sigma 3 is same as sigma 1, which is equal to 100 Newton per millimeter square, which is also tensile. So what I have done so far, I have not worried about the temperature change. I have taken into account only the load. Because of this 200 kilonewton, what is happening? Okay, so therefore the first part what I have done, due to 200 kilonewton load, what is happening? Sigma 1 is plus. Instead of writing tensile compressive, I write plus or minus. Sigma 1 is 100 and sigma 2 is plus 200 and sigma 3 is equal to plus 100. So all these are MPa or Newton per millimeter square. This is the first thing what I have observed. So now you don't worry about this 200 kilonewton. 200 kilonewton is not there. It is only a horizontal thing connected. This. Okay. So now what is that? Now I shall come to what is called as the temperature part, thermal stresses. Now the second part is due to thermal stresses. Now due to change in temperature, what stresses are induced? Due to thermal stresses. Okay, now let me see. Let me come back to the problem and read it. Okay, so the central rod is of steel and the outer rods are copper. Yes, fine, it's fine. If the temperature rise is 40 degrees centigrade, temperature rise is 40 degrees centigrade. Temperature rise, what is that? Delta T. Delta T is 40 degrees centigrade. Delta T is 40 degrees centigrade. Okay. Estimate the load carried by each rod, and by how much load will be, and how much this load will come down. Okay, that also is asked. Okay, so probably here. Then you also find out what is delta L. In addition to this, what is delta L? That is equal to anyone P1 L divided by A1 into E1. This also is okay. Okay, so P1 is 50 kilonewton. The length, this is 1 meter, 1000 millimeter. A1 is 500. E1. So I think 1 into 10 raised to 5. This also you find out what is delta L because of this. 1 mm. Okay. So this is 1 mm. Okay. So now, so for a while I shall remove as if this is not there. I shall represent as if this line only I take. Okay, only for the sake of indicating. Okay, calculation purpose. So what is that? Now what do I do? Any thermal stress. So what is the free expansion of 1? Free expansion of 1, which is also same as the free expansion of 3. I hope you all agree. Because both of them are copper, both of them have the same length, and both of them are subjected to the same change in temperature. Delta L1 is equal to delta L3. How much? Delta L1, that is copper alpha. Copper alpha is 1.8 into 10 raised to minus 5. This is alpha 1 multiplied by the length, that is 1000, multiplied by delta T, that is 40. This is so many millimeter, and this is the expansion. 0.72. Similarly, delta L2, free expansion of steel, that is equal to 1.2 into 10 raised to minus 5 into length 1000 and temperature change is 40. It's almost 2/3 of this. 0.24, 0.48. 0.48. This is 0.48 mm. Okay, so now you allow it. So you understand that the copper, so this one, the copper one will come here, and this is the same as this. Okay, this length what I have shown is 0.48. Okay, what about the steel? Steel will expand lesser than that, and steel say will come up to here. So how much is this? Sorry, I have written it wrong. This is 0.72. Copper expansion is 0.72 and the steel one is 0.48. This value is 0.48. Okay, the steel. In that case, this bar, horizontal bar, which is supposed to be, then it becomes like this. That is not allowed. Okay, therefore, they will have an understanding. What is that understanding? The copper bar says that I am not expanded to 0.72, I shall reduce it. And similarly, the steel will say I will expand a little bit, and then they will have compromise, and the compromise position of this is somewhere here. Okay, then in that case, what happens? This copper and this copper, they are subjected to what are called as a load P, a compressive load P. And what happens to the steel? The steel is subjected to also a load. How much is that load? If that is P, then it will not remain in equilibrium position. Otherwise, if you take this P, then this becomes P by 2 and this becomes P by 2. If you take this P and this P, in that case, this becomes 2. No problem. If you take this as P and P by 2 also okay. If you take this and P and this 2P, that also is alright. 2P downwards is equal to P plus P upwards. It will remain in a equilibrium state. Okay. So now, so this length, which is responsible of the expansion of the steel because of this 2P. So how much is that? That is application of PL by AE. The P is nothing but 2P. P is nothing but 2P into A. This is P into L. What is the L? L is 1000 only. Divided by area, that is 500 only. Into E of steel, that is 2 into 10 raised to 5. So that is nothing but this length. Then this will contract, no? So this will contract. This and this also same thing. And how much is this? This is equal to P as it is. L is how much? 1000 divided by area 500 into E of copper 1 into 10 raised to 5. So now you make use of that. Write down the equation. Okay, I start with this from here. This distance I shall write it as 0.48. Then plus this length. So how much is this length? That length, as I have written here, this is equal to this plus 2P into 1000 divided by 500 into 2 into 10 raised to 5. So I started from here and went up to here, and then I have gone here, that is nothing but here. Then I want to go further down, this value plus P times 1000 divided by 500 into 1 into 10 raised to 5, that is PL by E. So see here, this is where you started, went up here, then you have added the same thing here, then you have further added. So what is this total distance? This total distance is equal to 0.73. Okay, simplify this now. This is 0.73 send this 0.48 this side, and on the left hand side you can take P common. So on the right hand side, this is 0.72 minus 0.48. Okay, this P I have taken outside. This is 2000. This is 2000. 2 into 1000. 2000 divided by 500 into 2. Or you can simplify this also. 500 into 2, that is 1000. This cancels. Okay. 500 into 2, 1000. This is 2p. So p I have taken outside. 2 divided by 1 into 10 raised to 5. Plus p I have taken outside. This is 5,500 into this is 1. This is 2. So this is 2 divided by 1 into 10 raised to 5. Okay. Simplify this. You get p. This is so many.
6 kilometers.
6 kilometers, 6 into 10 raised to 3 Newton. Okay, so now, I would like to calculate what is sigma 1. Sigma 1 is the stress in this bar, which is copper bar. Before I proceed, first I decide what is it, tensile or compressive. Is it tensile or compressive? As P is compressing it, and therefore the stress I shall put it minus. Minus how much? P1 by A1, that is 6 into 10 raised to 3 divided by 500. How much? 6 into 10 raised to 3 divided by 500. This is minus 12 Newton per millimeter square. Please remember, this is also equal to sigma 3. This is also equal to sigma 3. And sigma 2. Sigma 2, what is the nature of the stress? Sigma 2 means steel bar. Steel bar is being extending, and therefore it is plus. Plus, what is the load? 6 into 10 raised to 3 divided by area remains same 500. Therefore, this is plus 12 Newton per millimeter square. And before I close, I also calculate what is delta L now. Delta L is what? How much expansion? What is the final position? This is the final position. This is what is its delta L. Earlier it was here. Of course, the remaining part I have not shown. And the same edge will come to this position. This is the final position, the compromise position. How much is this delta L? Delta L is equal to, can come back and see the diagram and identify delta L is this distance, that is 0.48 plus this expansion. This expansion is here. This is 2 into P. P is 6 into 10 raised to 3 into L 1000 divided by area 500 into E of steel, that is 2 into 10 raised to 5. This is so many millimeter.
48002.
48002. 0.48002. This is the expansion. Now what you are asked to find out what is the total effect. Please remember, in the first case we took only 200 kN and calculated what are the effects. In the second case we took only temperature change and we have not bothered about that 200 kN and find out what are the effects. Therefore, the net stresses, net result. Okay, now I shall find out
0.12.
point 0.12. 48 is not.
No. 0.12.
0.12. It should be more than 0.48. 0.48 plus 0.12 is it 0.6?
0.6.
It is 0.6. 0.6. Okay. So now what I call it as net effect. Net effect. So please remember, I am using what is called as principle of superposition. I found out the effects of only 200 kN Then I found out only the effect of due to only thermal stresses. Now what is the net? The effect due to both 200 kilonewton and also temperature change. Okay, what is sigma 1? The stress in the left copper wire, which is also equal to the stress in the last copper wire, sigma 3. What is that? So sigma 1 due to 200 kilonewton, it is plus 100. Then due to the second thermal stress, it is minus 12. You add 100 minus 12, this is equal to 88 Newton per millimeter square. What is this? This is tensile. The net stress. Because this is 100 tensile, this is a compressive, and tensile is more. And similarly, sigma 2. Sigma 2 due to load plus 200. And the second one also is plus 100 plus 12. Therefore, this is a 212 megapascal, and this also is tensile. And sigma 3 is same as sigma 1, that we have already written. And therefore, delta L total, delta L1, that is the first case, that is 1 millimeter. And the second one, it is 0.6 millimeter. And therefore, the total expansion is 1.6 millimeter. I hope you have understood it. And you may come across problems based on composite parts, only subjected to load also. Variety of problems are available in the books. I advise you to solve them. And if you have any difficulties, definitely we are there. We can help you. And all the best. So next time when we meet, we shall start a new topic. Hello, sorry I have to come back so soon. Okay, one small correction in this diagram. You can see here, due to thermal stresses, so what load this steel is subjected to? It is subjected to 2 times P. So when we wrote the equation and found out the signification, all that calculation we did, we calculated P as 6 into 10, 6 kilonewton. But this steel bar is subjected to 2 times P. And when I want to calculate the stress in steel bar, sigma 2 is equal to what is the force? Force is 2 times P. Therefore, this is 2 into 6. 2 into 6 into 10 raised to 3 divided by 500. This becomes 24 Newton per millimeter square. And hence, the net effect also is slightly changed. It is 200 plus not 12. It is 200 plus 24. This is 224 megapascal. This delta L, etc., all other things will remain same. Okay. This is small correction. Please note this. All the best.